recording. To the slides. So we've come so far. We've learned how to make our own functions, how to split up all of our code into multiple files, what's going on when we call functions, how do they know what to return back to, where to go, the stack, so important. We talked about references, which give us access to somebody else's memory, lets us make an alias for something that already exists. Oh man, it's great. We can change things when we pass along values by reference. And then we started learning how to make libraries and using multiple files. So that's where we stopped. Just a little bit left. I next want to talk to you about a special kind of parameter. So when you're making a function, you can pass along parameters by value, by reference. If it's by value, they're getting copied. If it's by reference, we're not copying anything. But we're allowed to touch somebody else's memory with the second we use references, right? What if we want that memory savings? We want the memory savings that comes with those references, but we don't want to accidentally modify those variables that are passed to us. We just wanted to not copy them. We wanted that space savings. So like we had our inc method for our or something, or increment by reference function, int reference I or whatever. And we did I++, and this legitimately changes somebody else's memory. Sometimes we just wanted to copy. We just wanted to copy this into our own function without like making extra space. So what if I'm like passing along a vector? This is a good example. If I'm passing along a giant vector, maybe size 1,000,000, I don't want to copy that, right? I don't want to use pass by value, call by value. I would like to use call by reference. But sometimes, like I'm making like a sum function on vectors. I don't want to be accidentally allowed to mess with each index of a vector if I just want to go and sum everything. So how can I pass it by reference, keep the space savings, but not allow myself to change it? The secret is to say const in front of the type of the thing. So it's a lot of words. Let's talk about it. So first of all, you know const already, right? We talked about const. It's a special kind of variable. It's just a variable that you can't change. So let's go back to code for that. Const.cpp. Here I am. Oh man, everything's crazy. Like I can make int x equals 42, and I could have said it's a constant, right? And that allows me to never change it again. Remember that? So this could also apply to function parameters, because what are those but special variables? So one important fact about constant variables is you can put anything into a constant, even if that thing is not itself a constant. You can copy into a non-constant variable, like this, const int y equals x. This is totally fine. It's taken x, making a new variable y, and that one can't change now. Right? I can still do x++, but that 42 has been safely saved somewhere else in y, and so I can't do y++. That part's not going to compile. All right? Cannot assign to variable y with const type. Can mess with x, though. All right? So that's what constant is good for, but you can totally put somebody else into a constant. That's not a problem. All right? Which means you can do the same with function parameters, because that's just another name for stuff. You can pass regular variables to functions if they accept const parameters. And the whole point of a const parameter is that parameter value cannot change. Ooh, that's nice. If you combine that with references, that means you're getting the space savings, but you're also not allowed to actually modify something. You can only look at it. You can only access its value. So that's beautiful. All right? So we want to use const references as much as humanly possible in our programs when we're making our functions, because it gives us the space savings, and it also makes it so that we can't touch anything, because maybe we're not supposed to, like for a sum function. So let's make a sum up all the values in a vector function. It takes a vector by a constant reference, and it goes and sums all the values, gives the sum back. All right? This hopefully should make sense once I do this. Let's include the vector library, and vector int v 1, 2, 3, 4, 5. So let's say I want to make a function that sums all the values in this vector. I'll call it sum vector. Here's how I want to use it. I want to give it v, have it sum up 1 through 5, everybody in the vector, and give it back. and then that'll be it. So it's called some vector. It takes a vector of ints, v, let's say, and it gives back an int. So we know, we're good C++ programmers, we don't want to maybe v was size 1 million, we don't want to copy it. So let's pass it by reference. Alright, so let's do our summing. Int sum equals 0. Let's go through everybody in v for every element in v. Sum, add that element into sum, and then return sum. That's the final answer. So that's all well and good. It will work. But I can mess up. I can accidentally do something wrong. So I'm calling some vector on this vector, passing it along there. Let's compile and run. I do get my 15. That is apparently this 9, 10, yeah, 15. That is the right answer. But look at what I can do right now. Look at what I can do right now. I can say, I can be evil. I can be like v at 0. Oh, you know what that is now? It's going to be 42. I'm just going to set v at 0 to 42. And that's messing with v, right? It's going to change the sum. If I see out v at 0, I will have made it 42. That's disgusting, right? This is supposed to sum the values, not mess with them. So you see that? So it made it 42, and now the sum is changed as well. So if you pass by reference, you're touching somebody else's memory. We don't like that in this particular case. But we like the space savings. All right, so we'd like this line to not be possible. Just the name of the function. It makes no sense for someone to do this in this function, but you could accidentally. So the secret is to make it a constant reference. Just put const out in front. And so it's going to make a reference. V will be a reference to mains v. Two things called v. One's a reference, the other is mains thing. So it's passing along. It's setting up the reference to mains v, but it's making it a constant reference. So I am not allowed to touch anything in it. I can access its values, but I cannot modify them now. I will get a compiler error, which is great. So assignment of read-only location. So once you make it a constant, it becomes read-only, the entire vector. Just for as long as it's part of that reference. So that's beautiful. So now this won't even compile. Everything is lovely, and we are forced to implement it correctly, or more correctly at least, and we still have one sitting where it should be. Right? So that's legitimately all I wanted to say about that. Just once you have references, you're allowed to change things. Sometimes you don't want to be allowed to change things, and so you might as well just mark your parameter as I don't want this to be touched. And you use const to do that. And the compiler will make sure you don't touch it. Any questions about that? Alright, not too horrible, I hope. That's the last main piece of functions. So now I just want to talk about some extra stuff that kind of go along with functions. Now that we can write functions, we can talk about cooler ideas. So I want to talk about the complexity of algorithms. So this section, if you would like to zone out, feel free. But I promise to not test you on it. It's going to be very, very helpful to understand it, though. Something to keep in mind once you get to CSCI 41. CSCI 41 is all about this particular topic. So I want you to have seen it once before you get there. You'll be extra good at it, right? So this may be something you have not thought about yet, but how fast is the program that I just wrote? Is it a good one? Is it the best possible program to solve this problem? So you can totally count the number of seconds that your program has run with the ctime library. There's a little stopwatch kind of function there. That's totally possible. And maybe it takes 5 minutes to run my long, complicated program or something. But this is the key problem. The same program running on my puny laptop is going to be slower than the same program running on these giant computers in front of you. Maybe it takes 5 minutes on my laptop. Maybe it takes 2 minutes on your giant desktops. And then microwaves have processors inside of them nowadays. They're very, very low powered. And so maybe if you run that same program on your microwave, it takes an hour. How can you compare in that case? You have to use the same computer every time? That's no use. That's not very helpful. Every processor is different. So we have to do better than that. Because some processors, they're 1.5 gigahertz. And what that means is it can do 1.5 little operations, tiny little CPU level operations per second. If you have a 3 gigahertz processor, it can do double that. It can do 3 billion tiny little CPU operations per second. All right? So that's unhelpful. We shouldn't be timing our programs. That doesn't really give us a good ground truth. So here are some nice ideas, though. Instead of timing stuff, just using a clock, let's count those operations that a CPU can perform, because across CPUs, they're doing the same thing deep down in the bare metal, the electronics. So regardless of processor speeds, some programs are still faster than others. There's still a better version of a program, even if you're running on a microwave. All right. So let's count those CPU level operations instead, all right, rather than timing stuff. So here are what I like to call basic operations. They're going to take one step of execution time inside of your CPU. All right. Some of these are a lie, but just don't worry. It will end up being a basic operation at the end of the day. It's not going to be too big of a deal once you get to CSCI 41. So assume that the following takes one step of execution time inside of your CPU. To do an addition, that takes one step of execution. It's one basic operation. To do subtraction, multiplication, division, modulus, all that math stuff. To do one of those, it takes one basic operation amount of time. To do a comparison, like check if one thing's smaller than another thing, if they're equal, that's also one basic operation. Let's count it as that. All right. Also, like assigning a value to a variable, that takes one basic operation. All right. Printing to see out, and this is where the lie is. This is technically not one basic operation, but let's count it as one in our heads. Printing something to see out, that takes one basic operation. So, for example, here's a couple lines. Int x equals, I don't know, y times the variable z plus 2. Something like that. So, and then C out x. Let's count the number of basic operations in these lines, and that will give us a good idea as to how fast it's going to be. Because every CPU will run those basic operations, even if it's in your slow microwave processor. All right? So where are all the basic operations here? Let's count them. We need to do a multiplication of two variable values, so that's one basic operation. And then once we have that, we have to add it to 2. So there's another basic operation. And then finally, once we have that value, we have to shove it into x. So assigning a value to a variable, that'll be a third basic operation. Do you see how I'm counting that? Does that make enough sense so far? And then, like sending something to C out, that's another fourth basic operation. So apparently, these lines, regardless of what processor you're going to run on, 1 gigahertz, 50 gigahertz, it'll take 4 basic operations inside. Okay? Some things are not basic operations, and you have to, they're made up of them instead. So summing all the things in a vector, that's not a basic operation because you have to loop, right? You have no clue how big your vector is, and it's a different number of operations depending on whether it's 100 things you got to add up or 1,000,000 things you got to add up, right? So there's a different amount of work to do for vectors of different sizes. So you have to zoom in and count those basic operations, all right? Maybe in terms of the size of the vector. Calling a function is not a basic operation because you have to run whatever is in the body of that function, right? And maybe it's a loop, and it's got to do a bunch of different things a bunch of different times depending on maybe the length of something. And another idea, reading a bunch of ints until the user types -1, that's of course not a basic operation because you're not sure when the user will stop. It's a bunch of individual basic operations to get the first value, put it into a variable, maybe save it in a sum or something. But it's going to be a loop. Anything that loops that you have no control over is not a basic operation. It's made up of them, though. Does that make sense? So yeah, these small things that you can say take one chunk of time, basic operations, right? And pretty much all single line statements, stuff like this, take one or a few basic operations. They're all basic, made up of them. Right? As long as they don't call functions that themselves loop, it'll all work out. Okay? We good with that idea? So this is going to lead to a way to categorize the speed of something. All right? So here's a little question for you. Give this a try. Humor me. Let's go to the written nice page, too. Oops. Feel free to work together as a group, though, and enter in your answer as a group. But here's where I want you to enter in the answer and have you calculate something. So here's a loop. See if you can count the basic operations in it. How many exactly will it be? It'll be in terms of n because you don't know what n is, so n will appear in your answer. But see if you can come up with the right answer. How many basic operations total will this loop take to run to completion? So try to analyze this, and then I'll show you my answer in a few minutes. And let me know if you have questions. All right, basic operations in this loop. And please write it down. This is a very weird stuff. So you have to remember how a for loop executes, don't you? It's like this line happens once, and then this gets repeated, this gets repeated, this gets repeated. How many times? You have to worry about all that now. But that will give us a number of how many CPU instructions this will take, regardless of the CPU. And that's a good way to categorize things and analyze them. I have to restart that box. Assignment, comparison. That's one basic operation. What's I++ doing? How many times will it run though? Take another minute or so. Get your best guess up in there. I see we got some answers in there. As a hint, n will appear somewhere in your calculation because you have no control over n. All right, that's my timer. Let's see what we're thinking. And I guess the spoiler is, honestly, the exact answer doesn't really matter. Once you get to CSCI 41, it's not going to matter. It's going to be, as long as you're close, you're fine. So that's good news for all of us, I think. You never have to actually look this carefully at your program to understand how fast it is. But nice, I see some things. N must appear somewhere. So 7n is a good thought. 7n, 3n plus 1, nice, nice, nice. 4n plus 1. Let's count. Yeah. Very nice. Do attendance, please, if you forgot. I'll stop that soon. But I like it. Yeah, that's looking right. It's going to be something times n plus maybe some extra stuff. All right, so let's start counting. All right, so for a for loop, this line, this initialization line, happens only once. So how many basic operations are in this one line? It's just the assignment. So it's just this guy. So this one happens once, and it's one thing. So it's going to be 1 plus something, all right? And then all of these guys repeat, right? Unfortunately. So we got to count, we got a comparison. That's one basic operation. And then I++, secretly, I equals I plus 1. So it's doing the addition and the assignment. That's two basic operations. Ooh. And then finally, outing things. If you if you split it up, like you're counting the I and the end-L, maybe that's two separate basic operations. At least that's how I will count it. And so it's like 1, 2, 3, 4, 5 things, but they're repeated. How many times? N times. Yeah, so this is all going to repeat from 1 to n, right? So this is happening n times, n times, n times, plus 5n. But that's not actually the full story. We have to run the condition one last time, right, to stop the loop. It'll make I plus 1, or make I n plus 1, and then it's finally not less than or equal to n. That will stop our loop. So it's one more time, one more condition we have to run to actually be done with the loop, and notice that we're finished. So plus another 1 there, and that gives us the analysis of 5n plus 2, at least on my end. But as long as you got close to that, you're right. Because the secret is, once you get to CSCI 41, what we do is we just notice the n here, and like, was it n squared? Was it log of n? We kind of like chop off the 2 because as n gets large, the 2 doesn't matter. So this is like, we consider this to be 5n. And then also, as you have like n squared versus log of n versus n cubed, the 5 doesn't really matter. And so at the end of the day, it's just some constant times n. As long as you can figure that out, that's essentially the speed of this program. Because, if you add one extra line, now it's like 6n, and that didn't really change much. So you don't really care about the constant either. That's the analysis. That's something you're going to get very, very good at in CSCI 41. I will not test you on it in this class, though. But you got to start at it. It seems like you're getting very close. Any questions about this? All right, and so we noticed that, like, as n gets large, the work grows proportional with n. And so, like, the graph of the amount of work you do depending on n is like a line. So we say this algorithm is a linear time algorithm because the graph of its basic operations look like a line, right? So yeah, the name of the game is, once you get to CSCI 41 and learn all this stuff in a very technical way, you're counting the basic operations as long as you are close. It works out. And then you end up writing, instead of like time tracking things and using a stopwatch, you create some mathematical formula for how fast the program is going to be in terms of like the size of its input. Like, we usually call that n. So here it's just whatever the variable was. It was n, in fact. But if it was k, it would be like 5k plus 2 or whatever. But a lot of the time we just use n as a generic variable there. But that's the game. And this will tell us how fast it's going to be on any computer. So just at a high level, let's talk about some algorithms and how they're faster than others. So like to add up 2 n's, if that's your algorithm, that's super fast. That takes what, one basic operation or maybe 2 if you want to return it or print it out. And we call that constant time. The algorithm takes a constant amount of steps, no matter how big those 2 numbers are. They're just sitting in int variables at the end of the day. Just 1 or 2 basic operations, constant time. All right? That is faster than, for example, summing up n numbers in a vector. Because if it's 100 things, you gotta loop 100 times. Or if it's 1,000,000 things in your vector, you have to loop 1,000,000 times. So it's proportional to the size of that vector. You're doing like some constant times those n things, right? To add them up, maybe advance your iteration variable, stuff like that. So we call that a linear time algorithm. It's growing like a line, depending on n. So that's kind of nice still. And then what about like if we want to draw an n by n box of stars? Like we get n from the user, like I want you to draw a 40 by 40 box of stars or 100 by 100 box of stars. That's a nested loop, right? How many times are you print a star? How many times are you printing out a single star? It's n times, yeah? So it's essentially n squared star printings plus some new lines and stuff, so it's some constant times n squared out in front. That is called quadratic time or polynomial time. So it's taken longer. It's a more complicated algorithm. Does that make sense? In terms of that input size. So this is more complicated than this is more complicated than this. And we can start categorizing algorithms in this way. And that's what we get really good at in CSCI 41. All right? So that if you start thinking about this now, you're going to do great once you take that class, I think. So I think that's all that I have to say about that. Are there any questions about analyzing algorithms? It's a good start. You'll learn more than you could possibly want to know in 41. All right. If we are happy with that, the final topic for the day that I want to talk about is just like making algorithms in general, because I'm going to give you a problem and it's going to be your job soon to come up with your way of doing it. Like there's not going to be a way, you're going to have to pick a way. So there's one way to break down algorithms into two separate pieces that sometimes works for a good chunk of problems out there. And so let me teach you about it. Sometimes your program will end up, or your algorithm will end up, involving like the idea of being in a certain state, like I'm in this state, or I could be in this state, or I could be in the checkerboard state. These are all the possible states that my program could be in, and then there are certain commands that move me around between states sometimes. Like I can go from this one to this one, or this one to this one, and then maybe from this one back to this one. But there's no way maybe to go straight from here to here. So if you can formulate your program in this way, there's a very cute way of writing it, I think. So if you can break up your program into a bunch of states and commands that move you around between states, it works out well. And so this is a design pattern, if you've heard of that. There's a bunch of different design patterns for programs or architectures for writing programs. And everybody likes their way, but I'll teach you one way right now. It's called using state machines, right? And it's like a good answer to this question. There is a way, if your program ends up looking like this, there's a nice way to build a good program that looks nice in terms of the code that's involved. And it's also very likely to be correct if you split it up into this set of two things, states and commands that move you between them. So that's kind of nice. So the answer is yes. Here's one way. It's called the state machine. All right. It is an abstraction over whatever you're trying to program. All right, over some process. It's very vague, and so this is going to be some vague examples, and we'll make them more concrete. Right. So a state machine, honestly, most of upper division computer science is circles and arrows. All right, so it's good to get used to them. So this is all a state machine is. It's just some circles with some arrows between them. So every circle is a state. Like here's a work state, here's a home state, here's a bed state. This is a state machine describing a very boring person's life, let's say. All right. So you could be either in the work state or the home state or the bed state. That is all you could possibly be in. And there's a concept of what state you start in, like when you get born or when the program begins. So an arrow just coming straight into some state, that's your start state. And then you can move around between states with these things called transitions, right? Little transitions. So here's an example scenario, like your person starts out in the home state, like that's where they're born, and then maybe it's time to go to work. And so they need to move themselves to the work state. And the only way to do that is to follow the transition called take train. Right? That's their one way of getting to the work state. You see that? It's kind of enumerating exactly what you can do, which is very powerful. And then once you're in the work state, like you do your work, and then it's time to go home. So you're going to take the train. Again, that's the only way to transition from the work state to the home state. You see that? There could be multiple ways, like maybe you drove today, maybe there's another arrow, but we just have the take train transition. And then you're at the home state. And then maybe it's bedtime, and so you want to go to bed. You want to transition from the home state to the bed state, and so the only way to get there is to follow the sleep transition. You see how that's working? This is a silly example of like modeling a person as a state machine. And then once your alarm clock goes off, you follow the wake transition, then you're back in the home state, and then you go to work again. But as long as you follow these transitions, you can move around between states. Like, all right, time to go to work. Maybe you go home for lunch, so you take train, then you go back to work some more, you go back home. And then maybe it's the weekend, and so you stay and you sleep twice before you go back to work. See how you can follow things? As long as you do what the transitions tell you, you can act in any order. But it's telling you exactly what you can and cannot do. All right? State machines are very powerful if you can break up your program into this idea, because they tell you exactly what you can do, which also tells you what you can't do. Notice how there is no way to go from the work state to the bed state straight there, as much as we might wish that we could. This is not allowed, and you can just read it off the diagram that it's not allowed and impossible. And that's a very, very powerful thing. You can start proving properties very easily about your programs if you model them as state machines. Okay? That's the idea. And here's a better example. Here's like an example of how like maybe a ride-sharing app works, like an Uber app or a Lyft app. So as far as the app is concerned, like it starts in the trip requested state, let's say. You ask to go somewhere and you have your Uber driver pick you up. And then what the app does, or what it's going to do, is it's going to go to the payment, it's going to follow the payment requested transition and try to go to the payment state, right? Because it's going to charge your credit card and make sure you can actually pay for this ride you're trying to get. And only once the payment succeeds does it give you that driver that you were looking at, right? If it failed, then you go back to the trip requested state and it tries to ask you for a new payment. Do you see how it is impossible to get a driver assigned unless you went through the payment state? That is super powerful. This means that the program will never like give you a free ride, which is bad for us, but good for that company, right? It's very easy to see if you can generate your program based on this. It's easy to make it correct. Do you see that? That's pretty nice. And then, all right, you're in the driver assigned state, you go somewhere, and then you go trip complete, and then the driver becomes unassigned, and then this whole thing loops over again, I guess. I don't know what these things are kind of trying to represent. Like maybe if the customer cancels, that will also unassign the driver. No need for a transition there, and like then it's the end of the trip. But this is kind of like the process model of a Lyft app. Like you got to go from here to here to here. This is the only way to get to the end of the trip. You got to follow that order. All right. I guess the driver could also cancel on you, so you go back to the trip requested state. But this is enumerating all the different possibilities for your program. And it's telling you what you can and cannot do. Like you cannot get a trip unless you pay. You have to go through here. That's very nice, very powerful. Easily provable as well. Okay? So hopefully this has convinced you that this is a good way to write a program, if you can model it like this. Any questions about that? So those are state machines. So you got states and transitions that move you around between states, potentially doing things as well in the process, like charging your credit card. All right, so here's another simple example. So if you could make a program like this, it would be very nice. So what you want to do, if you see a problem that maybe looks like this, you try to think about all the states that you can be in and all the actions on each state that you could take to move you around or potentially keep you in the same state, all right? So let's model you guys as a state machine. So as a teacher, I think of you as a state machine with two possible states. You're either in the learn state or the practice state, all right? And so maybe you start the class with nothing's been assigned on the first day of class, so your starting state is the learn state. That's our first lecture. And then as long as the lecture's not over, you stay in the learn state. It's totally okay to like follow a transition and stay in a state. No big deal. But like when I assign the first lab, then you transition from the learn state to the practice state. And then you just keep working there as long as the lab's not finished, and you stay there. Okay? And then once it's time for a lecture again, you transition back to the learn state. All right? So that's another example of a state machine. So like there's a concept of your starting state or your initial state, like that's the learn state for you. There's also a concept of a final state, where you should end up once you're done running the state machine, once you're done running inside of the state machine, I guess. And you mark final states with double circles. So this state, the practice state, is going to be your final state as a student in this class, because after the last lecture, there's nothing left to teach you, and there's just, you take the final, you're practicing one last time, and that's the state you'll end in this class. Does that make sense? So that's how you can model something with the state machine. This is still not a program. I promise to write you a program that uses a state machine by the end of today, but this is still just getting us used to the idea. All right? So now that we understand state machines, kind of, here's my question for you. There's no easy way for you to write this down somewhere, so just work with each other and come up with it yourself. But try to finish this state machine. Here are 3 states. It's a state machine for a traffic light, like the one outside on the corner. There are multiple correct answers, but see if you can figure out, like, what are all the different transitions between these states? What's the starting state, like when you turn the traffic light on, what should it be? What are the transitions? Can you go from, like, red to green? Sure you can. And what takes you there? What will you call that transition? Stuff like that. All right? So does the question make sense? Using these states tell me the starting state, and label all the transitions. How does a traffic light work? It really is using a state machine deep down. So see if you can figure that out. There are multiple correct answers, though, so give that a try. There are some transitions you cannot take. Some states you can't go straight from one to the other, right? Otherwise, people would crash. It's nice to do this with a state machine because you can prove that, okay, nobody's going to crash. The traffic light will work exactly like this. Another 30 seconds or so to think about it. But yeah, you can get as fancy as you want with this. There are plenty of operations on traffic lights. All right. So yeah, does anybody want to share a transition or something that they wrote down here? I think you could pick any start state you want, but the safest start state once you turn on the traffic light should probably show red, right? I think that's the best one in my opinion. But then what else? What would cause a traffic light to go from red to green, right? That's definitely a transition that you could take. What would you label this as? Yeah, cars approaching, or car is approaching, and it's like been waiting there maybe. Car approaching / waiting at least a minute or something. So you got to give other people a chance too, something like that. Or then in addition to that, right, you also have to make sure that no other lights are green right now, unless it's the one on the other side that's not going to cause any problems. No other lights green. That's kind of what you're looking into there. That makes sense, right? And then so it's green for a while, and then can it go straight from green to red? Is there a transition that way? No. So it goes from green to yellow, and then from yellow to red. So like, I don't know, maybe it stays on for 30 seconds or something. 30 seconds later, it becomes yellow. And then it doesn't stay yellow for very long. Apparently, it stays yellow longer when the speed limit's higher, which makes a little bit of sense. So maybe it's like on this particular street, it takes 3 seconds for it to go from yellow to red. So that kind of makes sense. That's a good state machine. Are there any other states or transitions that we thought about? Those are kind of the default ones. It can stay in blink red, right, sometimes. It can stay in the red state if there's like a power failure, electrical failure. It just starts blinking red. Becomes a stop sign, right? It could also blink yellow. That's a possibility. But you can get as fancy with this as you want, but notice how you are forced to enumerate every possibility, which way it could go, what takes you there. It's a very powerful thing. And so people who write mission critical software like traffic lights that might kill somebody if the software is wrong, or like flight control software in an airplane, they are absolutely doing this. They are writing out every possibility and proving that only the ones that they want to have happen will happen. It's very nice, right? So this is one way to make correct code, and the code ends up turning out pretty nice as well, I think. So yeah, this is why I'm teaching it to you. Any questions about that? All right, for my last example, I finally have, I'm going to do some code. All right, so let's make an example where we use the state machine to count all of the words in a string. And so this is exactly what like Microsoft Word is doing or Google Docs is doing when you ask it to count your words. It's going to run this algorithm essentially, right? And so essentially, you have a string somewhere, like you got a line from the user, and you want to count all the words in it. And I promise it is not an easy task. Because you might think for a second and be like, oh, the easiest way to count all the words in some string is just like, let me count all the spaces. Because spaces are supposed to separate words, right? And so maybe like there's one more, count all the spaces and add one, and that's the number of words. That is not always true. Because what if the string was like, hello, comma, space, world, exclamation point. And then the user typed like 3 spaces here. That throws off everything, right? So it is not the easiest task to solve this problem. Blah, space 42. So maybe that's our string and we want to count all the words in it. It's going to work out very well if we make this a state machine. So let me show this to you. And so the trick is, we're going to make a state machine, and we're going to feed it every character of this line one by one. All right? And the trick is going to be to notice that sometimes those characters will be white space characters, which mark the in-betweens of words, and then some of the characters are not white space characters. You can also type a bunch of new lines, right? When you're typing an essay, there's new line characters and tabs as well as spaces, so we got to count those too. And we can use the isSpace function in the CC type library to just tell us, was this character, whatever it was that space, some space character, like new line, normal space, or tab. We'll use that. And then the key idea that's going to inform the way we make the state machine is that white space, once we see it, it separates words. And then every non-white space character that we see, it's either part of an existing word or it's the start of a brand new one. And that will have us count stuff, right? So we'll make like a count variable, we'll increment it when we see a new word. And so that's how it's going to be, right? This, by the way, is the one thing I remember from my CSCI 40 class when I took it at Fresno State. So my professor taught state machines, and he taught exactly this algorithm. So I am passing it on to you, right? So that when you become a teacher, you can teach it as well. So you can be in one of 2 states. Here's the secret. Here are the 2 states that your program can be in as you're trying to count all the words. You can be in the outside a word state. You're sitting outside of a word right now. Or you can be in the inside a word state. Those are your 2 possibilities, right? And you're going to run the state machine through every character of your line or your string. And since you haven't read anything at the start, your starting state is outside of a word. We're not sitting inside of a word right now because we haven't read anything. Okay? And then, here's how we're going to move around. We're going to look at every character, be like, oh, there's an H. We're outside of a word right now, but the H is not a space, it's part of a word. So we're going to transition. Do you see that? You see the H, if you see a non-space character and you were outside of a word, well, you're inside a word now. Does that make sense? Non-space. You saw that H, you have now transitioned to be inside of a word. Now I'm part of hello. And once I see the E, the L, the O, the comma, those are still part of that same word. Do you see that? And so if you see non-space characters while you're inside of a word, you are still inside of a word. So you remain there. Boop. Non-space. Cool. And then, like, eventually you're going to see the space here. So you were inside of a word, you were reading hello, but now you see a space character. You are no longer in a word, you're in between words now. So the second you see a space character and you were inside of a word, you're going to transition to outside of a word. Does that make sense? And then if, like, maybe you were over here, you saw a space, and then you saw another space, you were still outside of a word, right? If you're outside of a word and you keep seeing spaces, you remain outside of a word. And so at each state, either you see a non-space character or a space character, and we've just said exactly what to do in each case. Does that make sense? And now the trick is, the thing that makes it like an easy algorithm come out of this is one of these transitions notices a brand new word. Do you see which one? One of these arrows notices a brand new word, and we should count it right then and there the second we see it. Does anybody see that transition? Which one notices a brand new word? Very good, yes. So if we were sitting outside of a word, like we were seeing a bunch of spaces where we haven't seen anything yet, the second we see the first character of a word, we take this transition right here. This is the special one. If we just always added 1 to a counter right there, that would count the words correctly, regardless of how many times the evil user put spaces between things. All right? So that's the secret. If we made a count variable, started at 0, of course, and we just, every time we take this particular transition from outside to inside, if we add 1 to count right there, that's when we notice a new word, and that will correctly count all the words in our line. All right, so let's run it. Let's run our state machine through this example line, and then we'll code it up. So, all right, we start outside of a word, so we're sitting in the outside of a word state. We see the H character. H is a non-space character, so we will follow this transition, and we are now sitting inside of a word. So we follow this transition, and we add 1 to our count. That was the special one. So now we're in the inside of a word state, and we see a bunch of non-space characters, the E, the L, the O, the comma. We just keep on following the non-space transition. We're still inside of that same hello word. Okay? But the second we see a space, we take this transition. Now we're in the outside of a word state. So now we're sitting in outside of a word. We see the W, though. That means we're inside of a new word, because we were outside, we saw a non-space, now we move to inside. Does that make sense, how this is running? So it's the characters that are going to run this state machine for us. So there we go, we see the W, we see the O, we stay in the inside of a word state, it's still part of the world word. RLD, exclamation point, those all keep us in the inside of a word state. And then we see a space. We follow the transition then, because a space character takes us from here to outside of a word. So now I'm in the outside of word state. I see the next space. I'm still in the outside of word state. I see the third space. I'm still in the outside of word state. I have not changed my state until I see a non-space character. So the second I see the B and I was over here, that's the first character of a brand new word. I'm transitioning from outside to inside, and that will give me, yay, a brand new thing to count. And there's my third word, and the L, the A, the H, those keep me inside. One more space takes me to outside. And then the 4, it's a non-space character, that's a new word. So I take this transition, now I'm back in the inside of a word state. And then I see the 2, and so I remain in the inside of a word state. So the state machine ends in the inside of a word state, which doesn't really matter. All we cared about was keeping track of the count. And the count has correctly counted the 4 words in this line. See how that's working? It's kind of nice. Kind of very succinct. An easy way to count the words. And so this is what Google Docs is doing, Microsoft Word is doing. So let's code this up. Let us create this state machine, and let's do it fancy. Let's make it a library, a count words library. Let's make separate files. Let's practice everything we've learned about. And then I promised to stop this, I think, so I'll stop that now. And let's make a new folder for all this. I'll call it count words. So I'll work inside of here. Count words. And let's see. Let's make a header file first. What do I want to do? What's the function that I want in this library? So I'll call it countwords.h. Remember your header file guards to protect against infinite inclusion. Oops. And then we want to make our function like this. Let's have it be called count words. It takes a string S, and maybe the string is a million long. It's like the entire works of Shakespeare or your very long essay or something. let's pass it by reference, but we just want to count the words in it. We don't want to change any of the characters, so let's pass it by constant reference. Ooh, that'll be nice. And then what should it return? It should return an int, the number of words in that string. Okay, so that's going to be the declaration of the function we're about to write. Does that make enough sense? So one thing, first of all, we need the string library, include string. We want the string type. One thing I do want to warn you about is header files, you're including them in other files, right? You're going to number sign include countwords.h somewhere else. And so what you can never do is you can never use namespace standard in a header file. So I'm going to do this in all caps. Do not use namespace standard in a header file. ... Or exclamation point, exclamation point, exclamation point. The reason why is because maybe the person who's including you did not want to use namespace standard. The second you say namespace standard in your header file and they include you, they're copying and pasting this entire file. And so they themselves are now getting namespace standard included, used, when they didn't want it. So you cannot ever use namespace standard in a header file because it's going to be copied and pasted to somebody else's file and maybe they did not want to use it. They wanted to keep it all separate. So you are forced to say standard : string here, if you remember that. Okay? So that's important. You can never use namespace standard in a header file. Can't use any namespace, in fact. What's that? What's that?
Why do people like writing it like that?
This thing?
Yeah,
what?
Using namespace. Why do they instead prefer that method?
Sometimes they made their own string type. Okay. They wanted to use that one, not the standard libraries one. And so then there would be a clash had you use the namespace standard. Yeah. The whole point of this thing called a namespace, which I will talk about later in the class, is so that you can have different things with the same name. Like you can make your own string type. You can make your own vector type. Make your own cout even. Yeah. Good question. Any other questions about this? So we can use namespace standard all day long in the implementation file. That's just for us. But for header files that are getting copied and pasted other places, it is a no-no to use namespace standard there. Okay? Let's make now a main.cpp that uses our library. So we have yet to implement it, but let's include our library, countwords.h. And let's pretend that we have it already. Let's get a line from the user. And notice, I don't have to include the string library because it's being included from countwords.h. I can just start saying string, let's get a line from the user with getLine. Cout, enter a line of text. Boop. Then we'll say getLine, cn into line. GetLine, by the way, it's passing line by reference. Now you know how it's messing with the line variable. What else? Then we'll be like cout, count words on that line. Okay. And then now all that's left is to implement our library. So let's have a countwords.cpp that takes this and implements it. And so now I can finally show you why you include your header file in your implementation file. Include countwords.h. This is going to include the string library for us. We don't have to do it separately here now. You just include your header file. You get everything that's defined there. You are totally allowed to use namespace standard in an implementation file anywhere. That's just for you, the implementer. Nobody cares. So I can get rid of the standard : now in this file. It's totally fine, but not the header file. All right? So, okay, the secret is, let's see, how do we want to do this? I guess I don't really need this extra thing. The way to implement this state machine now is you can't make circles and lines and arrows inside of C++. The best you can do is just keep track of what state you're in. This is how we're going to implement the state machine. We're just going to keep track of what state we're in. All right? So let's just remember what state we're in with maybe a string variable. What is our current state? Well, make it all caps or something, outside. Or you can use a number to encode, 0 for outside, 1 for inside. But we need to keep track of what state we're in. We're programming the state machine in code right now. So we need to know what state we're in, and based on that state, we need to take our next input and move around the state machine, take our transitions. Okay? So we start in the outside of a word state. We're just going to use a variable to keep track of what state we're in. And then our count starts at 0 because we're counting all the words. And we're eventually going to fill up count and return it. Okay? And now the secret sauce is in the middle. So we want to run the state machine on every character in S, in the string that we were given. We're allowed to look at it, but not touch it. Okay? So, let's go through every index in that string. For int I equals 0, I is less than s dot size, I plus plus. So at every index of S, we have a new character. So like current char equals S at I. So that's my current character I want to look at and run through the state machine. And now, to run the state machine, it depends on where we are, right? Either we are currently in the outside of a word state, or we are currently in the inside of a word state. And we do different things depending. So we have to check that first. So if the state right now is outside, we do the outside transitions. Otherwise, we can only have one other state, so let's just use else. Otherwise, the state must have been inside, right? We'll use that to encode inside. And so if we were in the outside state, follow its transitions. Otherwise, if we were in the inside state, follow its transitions. Does that make sense? So we got to split it like that. And so if we are in the outside of a word state, and the character we saw was a space character, we stay here. All right? So if we are in the outside of a word state, and we just saw if the current character is a space character, and that is CC type that tells us that, right? So include CC type for is space, oops. If the current character is a space character, it'll give back true or false, depending. So if is space of current char, that's a true thing. If the current character is a space character, then, so notice what's going on, two if statements. So if we're outside, and this is also true, if we were here, and we saw a space character, we remain outside. So honestly, we didn't even need this body, have an empty body, but just for us, we'd be like, keep the state outside. Technically, I don't have to do anything because it's already outside, but who cares? Otherwise, if it wasn't a space, it must have been a non-space character. And so this is our secret counting transition, right? We were outside, we did not see a space character, so we're here. So that means we are following this transition. So our new state better be inside of a word, and we also want to add one to our count. See how I'm implementing the state machine slowly but surely? So if we didn't see a space character, our state, we're moving to the inside of a word state. We just saw a new word, the start of a new word. And we would like to count plus plus here. We just saw a brand new word. And so that is implementing this particular transition. Any questions about that so far? So I just implemented the outside of a word state's transitions. Every possibility, whether it was a space or a non-space, I told it exactly what to do, what new state to go to, and then also any extra stuff, like adding to the count. And then finally, we have the other side, the flip side. If the state was inside, if we were over here instead, we do different things depending on if we saw a non-space character or a space character. It's almost the same, we just don't add to the count. So if we are inside a word and we saw a non-space character, we remain inside of a word. We don't add it to the count anymore because we're part of the same one we already added to. Or if we saw a space character, we're going back to outside of a word. All right? Because we're inside now. We saw a space, that takes us outside. So it's pretty much all of this, all over again, except we're not adding to the count anymore. So it's that. Do you see how that's going to implement it? Like if we saw a space, then we follow this transition, takes us to outside of a word. Or if we saw a non-space, we remain in the inside of a word state. So technically this could have been blank or empty because we're already inside, but it's good for us as programmers to remember what's going on. It's helpful, I guess. So that will correctly move us around in the state machine. This big long if else. Sorry, it's so much code. Let's see if I can get it all on the screen. So here I am going through the entire string, every character, running it through the state machine, and here's the transition where I found a new word. I add to my count of words. Any questions about that? That should more or less do it. We're filling up this count variable. Here we are returning it, and we're using it. We're using it in the main file. So let's see if I can split screen all this. So here's our implementation. Here is our header file. Poop. And then here's our main function. That's like, we're including our library, and then we're running count words on it. So let's compile everything together. G++, give all the implementation files, countwords.cpp, main.cpp. Don't need to give the header file because it's being copied and pasted. We're good there. And let's call the final output executable file main or something. So /main, hit enter, enter a line of text. What do we say here? Hello, comma, space world, exclamation point, 3 spaces, blah, space 42. And I can put extra spaces too. Doesn't matter. Run the state machine. Yeah, there were 4 words there. It figures it out. It ran that state machine, took the string with our function, gave back the number 4. Yay. Any questions about any of that? So this will work for any string you want to give and type. That's beautiful. All right. If we are happy with that, let's do one last thing. Let's make a test for our count words function. I think that's going to be our last full circle thing. We'll remember everything that we learned. So let me steal the assert true function, and we'll put our test in the main.cpp file. So where did I put lecture, let's say lecture 12? Sum of squares, maybe? Is that where I put tests? Sum of squares? Probably main.cpp there. Let's see. Nope. How about lecture 11? Testing.cpp. There we go. Assert true. Steal. Paste. Oops, not there, but there. So now I have my handy dandy assert true function. Let me comment out all these things. Let's kind of turn this idea into a test. We'll make a test count words function. Alright, so it's just a void little function that does a thing for us that runs a test. And so I will make a string s equals hello, comma, space, world, exclamation point, spaces, blah. Any space counts as space, so like new lines, tabs, doesn't care, 42. There are 4 words here, right? So we need to assert true that if we call count words on S, we get back 4, all right? So count words in a 4-word sentence. So do you see how that's going to be our test for this? You make up a string, be like, all right, I will hand count these. There are 4 words here, so that's what my count words should have given back. That's what I want to assert. And so let's compile everything and rerun, and hopefully we have a passing test. Yay! So there we go. We got a 4-word counting test passed. And essentially your job now as a tester is to make as many tests as you need to convince yourself that your program is correctly counting the words. So a good corner case to check out and watch out for is like counting all the words in an empty string or a string with just spaces. That should be still 0 words, right? This is like to protect against that naive solution of just like counting all the spaces and adding 1. That's the number of words. So there are 0 words here. It better give back 0. And our implementation, if we did it right, it should give back 0. And so that one passes as well. So you just make a bunch of these assert true calls. You come up with scenarios and ensure that the output of your function matches what it should have done for that scenario. All right? That's a couple tests. Any questions about any of that? That's a good review of everything that we learned, I think. And we passed that string by constant reference, too. It's beautiful. So we can't mess with it. Like if I say s at I, make it a space character or something, this will not compile. Lovely. All right. So yeah, we made it. This is a very long set of slides on functions. There's a lot to talk about, but we got through them all. Yay, go us. So, yeah, it was just a lecture for the day. So the rest of the time is yours to work on stuff that is already out.